In the past, famous researchers spent most of their lives in oblivion. Does this still happen today? It's really easy to reassure ourselves presently when we can't see into the future. If something is currently available and is being squashed, it may take decades or a lifetime to find out the truth. But there are some very troubling signs that we can see today, and I will talk about 3. The first is, if you ask most academics about their experience promoting especially new ideas, and especially recent PhDs trying to establish themselves, and new research, and obtain a job, publish publications, get grants, they will likely tell you research is very political, as such talented researchers leave academia in disillusionment. And this sounds so surprising given the contrary messages promulgated by grant agencies, departments, and universities, who say they are furthering research and are up in front and central to progress. The second one is a study motivated and titled Evaluating the Max Planck Quote about the One Death at a Time Business, which literally evaluates how premature deaths of elite scientists, superstars in their field, affect the dynamic of scientific discovery, showing that his quote seems true. Following such deaths, scientists who were not collaborators with the deceased star became more visible, and they were able to advance novel ideas through increased publications within that field, and those non-collaborators tended to be new to the subfield, suggesting it is true. Star scientists and their collaborators are highly interconnected, and they may hold back research of others, making it harder for those with new ideas. While some researchers have a difficult time showcasing and publishing their new results, others are allowed to publish research results which simply don't hold up. And that brings us to the third and most worrisome sign, known as the repeatability crisis. About only 35% of research is statistically replicable. This is in most fields. How can it be? This research passed statistical analysis and the all-holy peer review. Now, according to a poll of 1,500 scientists, 70% of them had failed to replicate at least one other scientist's experiment, and 50% had failed to replicate one of their own experiments. In medicine, a 2012 study of preclinical medical cancer found that only 11% of those studies could be replicated. In psychology, a 2015 empirical study attempting to replicate 100 previous studies from 3 high-ranking psychology journals found overall that only 36% yielded statistical findings compared to 97% of the original studies. And these included 28 classic contemporary findings in psychology that are taught in textbooks. And overall, 14 of the 28 findings failed to replicate, despite massive sample sizes. A newer 2018 study sought to replicate 21 social and behavioral science papers from the most prestigious journals of nature and science. It was found that only 13 of the 21 could be successfully replicated. In neuroscience methods, specifically fMRI, studies can be overcomputed. This was left unaddressed in the field. That is, until some researchers proved their point by taking a dead fish and putting it into the fMRI and getting results that were statistically significant. This study was never published. Many findings like this aren't. But it did get an Ig Nobel Prize award. And a very recent study which proactively gave raw data to neuroscience fMRI groups to process and make conclusions about it found that the data was interpreted into different results depending on the group's processing. So this continues. A 2019 study, which focuses on computer science, showed that of the studies published in top conferences in computer science, on average, less than 40% of the articles were reproducible. For this discussion, I will describe reproducibility as the ability to read an article and obtain its supplementary resources, including computer code, when applicable, when available, and reproduce the experiment. Replicability as being able to, in addition to repeating, to obtain the same or better statistical performance or results. In computer science, algorithms are often compared to each other. So repeatability and replicability are very important to reliably compare between algorithms. But human factors behind competition can make this difficult. The study above showed that of 18 algorithms, only 7 were repeatable with reasonable effort. The reasons for not being able to repeat can include not having the algorithm described or written well, or the test data not available. In a fierce, all-out competition, there may be a benefit for not having those available. How can the algorithm be criticized if it's not available? Other reasons are simply the claimed results of their algorithms was not obtained. But even in the repeatable articles which the results are obtained, much of the poor performance of compared algorithms were not replicable. When replicating the comparison algorithms did better than reported. In the study of the 18 papers, they did not find an algorithm that is better than what's already out there. To try and address some of these problems, there is a push to use fixed data sets and tests, like ImageNet for computer vision. There's even a service to provide fixed tests, such as Kaggle, that is not under the control of researchers themselves. The algorithms are sent and automatically all algorithms are tested against the same data sets. But then the focus can become on optimizing algorithms for those tests, and the tests aren't perfect. The underlying tasks that the tests themselves were designed to emulate are no longer relevant because the algorithms game the imperfections. So algorithms optimized for specific tests tend not to be optimal for real-life applications, but are again hard to give up because those also benefit certain researchers. Thus, there's no good solutions of how to fairly test algorithms without the human factors. The computer science findings are especially concerning since the field is endowed with some of the best resources, and the algorithms are implemented on a controlled computer environment where repeatability should be less of an issue. When the results are difficult to repeat, the state of the art in the field becomes muddled because it discourages those trying to propose new ideas. So both reproducibility and replicability are very harmful. Clearly, replicability harms the credibility of science. The funding that got wasted, the publication process, researcher time, taxpayer resources, and the wasted time going down wrong paths. But the reproducibility issues are harmful as well, since it's a form of obfuscation, making things more difficult for competitors. And it affects new and underfunded researchers more because they often must compare their algorithms or methods to existing ones. But then they waste their efforts on not being able to repeat and compare, getting slowed down and inhibited. The replicability and repeatability crisis is far greater than a few isolated papers and includes virtually all fields. It's not simply a problem with statistics or scientific methods, as most academics are educated and practice them. So it's unacceptable to have 70%, 60%, 50%, even 25% irreplicability rate. The highest statistically acceptable value is 5%. The statistics are designed this way. So anything else suggests it's a significant problem. So could the same environment that blocks new research, encourages suboptimal results seen in the repeatability crisis, also generate troubled behavior affecting other aspects of academia like newcomer complaints? Moreover, since they do not seem to be new and have existed in the past, why have the underlying problems not been spotted and addressed by the most educated people on earth?